if I understand correctly, Matthias Forkel cannot be here, so the talk will be given by Martin M.Thurner, so the second talk this day. And then
again, I think it may take. Now the presentation opens because Matthias put a lot of global maps into his presentation. Yes, Matthias cannot be here today, but for good reasons. He became a father very recently, and so I will give the talk on behalf of him. Also, I'm not really an expert on this topic, but I will try to answer your questions as best as possible. But if you have very detailed question at the end, you can also contact him via email. So, and I hope we can also contribute to the questions Ranga was asking at the end of his talk, but I think we cannot fully answer them up to now. Okay, so Matthias is also a PhD student at our institute, and he's also working on the Greening Earth, and he's integrating multiple satellite observations in order to optimize technology in the LPJ GV2M. Here you can see another map showing global greening and browning based on the GIMS NDVI, in this case for the last 30 years. And we see overall there is more greening present on the land surface, especially in tundra regions, for example in northeast Siberia, but there are also some smaller areas where browning occurs. And but now we are moving from NDVI to FAPAR because we were integrating FAPAR data into the LPJ model, and here first of all the two different data sets, GIMS and from GeoLand, are compared to each other. And we can see that they show not such a good agreement or a very bad agreement actually, in some of the boreal forests and in tundra regions, for example. But here in the Amazon, for example, also, but this is also due to the weak seasonality in these regions. Comparing to the LPJ managed land model version, we can see that in general the GIMS dataset seems to agree better with the LPJ model in many of the boreal and temperate forests, but there are also, for example, in the grassland regions, the LPJ model does not compare very good compared to both of the datasets. So finally, when looking at the FAPAR trend averaged here for all the boreal needleaf evergreen forests, we can see that there's a large jump in the GeoLand dataset due to the dataset is originating from two different centers, ADHR and Spot Vegetation. And this is also one of the reasons because from now on the GIMS dataset was our decision to use this dataset for optimization of the model. So the research questions underlying this analysis are: which are the observed dynamics in greenness, and are they environmentally plausible, and can they be reproduced by global vegetation models? How can these models be improved by using satellite data, and which are the environmental controls on vegetation in greenland? This is a simplified representation of the LPJ photosynthesis technology and FAPAR module. And here you can see that the FAPAR is dependent on the model of land cover of phenology, which has a value between 0 and 1. 0 means no leaves at all, and also dependent on albedo. And there are also several feedbacks in this model. For example, because it's a dynamic vegetation model, there's also a feedback on land cover. Two different phenology schemes were applied here. The original phenology, from now on called OP, with several structural limitations. So, for example, it is not at all dependent on water and light availability. And then Matthias implemented the growing season index phenology into the model. This is what I want to explain now. So this is an adaptation of the growing season index concept from Jolly et al. And it was already used for model optimization by Steffi et al. Before, but here it was modified. So for example, here are now logistic functions used instead of threshold functions. And there's one function for the phenology depending on core temperature, on heat stress, on light availability, and also on water availability, which is here depending on soil moisture, amongst other things. And the combination of these four phenology functions, they are at the end multiplied, and phenology is calculated based on these four functions. So now this is the data integration system which was used here. So the FAPA data from GIMS was used for the optimization, while the GeoLab data only was used for evaluation purposes. So the phenology parameters, 3 for each of these phenology logistic functions I was showing, are optimized in a genetic optimization algorithm. And additionally, in order to account for the feedbacks in the LPJ model, there are also data sets on GPP from the model tree ensemble data sets from MPI, and also in modus albedo are used to in the cost function for the optimization. I also want to add that here is monthly, 30-year monthly FAPA data are used for this optimization. 10-year monthly albedo data, and the 30-year mean GPP data. Then several experiments are done. So, for example, the model is run with dynamic vegetation, but also prescribed land and tree cover. And burnt area is also prescribed in order to avoid an influence of the fire module in LPJ. At the end, the model performance is also evaluated against independent data, including evapotranspiration data, biomass data, soil organic carbon data, and atmospheric CO2 concentration data. Yes, first of all, Matthias implemented here the grid optimization at grid cell level, and then you have a spatial variability in the optimized parameters. But at the end, he was optimizing the model for different PFTs, so using 30 to 50 grid cells for each PFT, and at the end, we were able to derive a unique parameter set for entire PFTs. These are results of the study. So first of all, concerning the monthly FAPA dynamics. So you remember we've been optimizing the model using monthly FAPA data, and you can see a very nice improvement here. On the left side, we have the correlation between the GIMS data set and the original phenology model, and on the right side, between GIMS and the improved growing season index-based phenology. Yes, and you see that in the original model, for example, in grasslands, in the Sahel, or also in Australia, there was a wrong similarity, and now we match the FAPA much better. Also in tundra regions, there's only in evergreen broadleaf forest, we see no improvement due to the seasonality there. But also, we improved also the model in terms of annual FAPA dynamics. You can see here, so there was, for example, a relatively weak agreement in the tundra
high gas transition zone and is now improved. And also for other PFTs there was an improvement. And overall in 37% of the land area we matched better the GIMS data with new implemented phenology. Yes, in terms of trends, this is a bit more difficult, I think. But yeah, here we can see VR means always browning, NO means low trend, and GR greening. And this is like a confusion matrix between GIMS and old phenology and GIMS and new phenology. And we can see there are slightly less opposite trends with the new phenology here. In the maps, only significantly trends plotted, pixels with significant trends. Yeah, the general patterns of the trends are reproduced, but across models. So let me try to explain this figure. So in this case, G is greening, V are browning areas. This is boreal forest greening areas and boreal forest browning areas here in North America. Some greening areas. Try to concentrate on the red line always. This is a GIMS data set we were optimizing again. And blue is geoland. This is the old phenology, dynamic vegetation, old phenology with projected land cover, with prescribed land cover. This is the optimized old phenology, and this is the new phenology with dynamic vegetation and prescribed land cover respectively. And for example, if we are looking here at the side, we see a very nice match between the GIMS data set and the new phenology, dynamic vegetation. This is also, for example, true here. So you can see that definitely the new phenology is better to reproduce the trends than the old one. Yeah, then we also compared the model with all the new phenology to the biomass data set. This is a composition of our biomass data set for the North Hemisphere and the Sachi biomass data set for the tropics. And in terms of the absolute difference in biomass, we can see that with the old phenology had a much larger difference, for example, in boreal forest and tundra regions, which decreased significantly, and also in some tropical forest areas. We have the patch. But of course, one cannot expect from optimizing the phenology that get the biomass right now in the model, but that there is an improvement through this model optimization. Yes, and this is also plotted here on the right side, differently for human areas. The red line is data, and the model with the new phenology is the violet line. And you can see that it's, at least in most of the areas, now with an uncertainty of the data. Of course, there's still a lot of the difference. Yes, then we're also looking at controls of vegetation greenness. So, as you know, FAR is controlled in the model by land cover and the different phenology functions and albedo. And we can see here a nice plot of the seasonal controls on FAR. So FAR, the model FAR is the black line here, and the seasonal controls are plotted here. And you can see lower the value for this seasonal control function, the most it is limiting the FAR. So in this case, for tundra regions, it's in winter, as we would expect, light, but cold temperature, and cold temperature is the most limiting one, almost for the whole yeah. And in spring, for example, when water is frozen, it can also be a limiting factor, but for example, stress is never a limiting factor in the tundra region, according to this analysis. It's a very nice realization of the seasonal controls on FAR. So this is the GV composite. In the red channel, we have water stress in the or water limitation. In the green channel, light limitation, and in the blue channel, emission on power through core temperature. And you can see that in winter times, core temperature together with light is limiting vapor in the northern hemisphere boreal and temperate forests, while, for example, tropics, depending on the season, water can be in the dry season the limiting factor. This is moving with the disease to northern hemisphere. Yes, and here Matthias did experiments on the controls, on the temporal dynamics of mean and data in this case. And here he was doing some factorial model experiments, so was removing the effect of in each experiment of one limiting factor and showing how much, looking much error will increase in the data. And we can see that concerning the most important factor on FAR, that wind and light, so-called light, are the most important factors in the northern forests, and in the crops it's mostly T-max. But also very interesting concerning the second most important factor, which is very almost all over, not in the northern boreal forests. And now I want to conclude this presentation. So you've seen there's a poor agreement between the GIMS and data sets in terms of annual availability and trends, but we get to use the GIMS data set for reasons I have given. And the BJ was not possible using the scheme to reduce the vapor dynamics, especially in grasslands and in forests, because there are several structural limitations, and also optimization did not help. With the new energy scheme based on the growth season index concept, we were able to reproduce the vapor dynamic much better in many biomes. Also, they was improved regarding GP, albedo, and also study biomass, tree cover, soil getting. That are once not shown here in this presentation. Yes, all large-scale trend changes were at least to some extent reproduced by the model, and they contribute to the control of the greenness was very heterogeneous in space, but also varies in time, and we identified water ability and heat stress as important controls on the vapor dynamics, which can have almost all biomes. Okay. Yes, thank you for your attention again, and yeah, I'm here for discussion.